Hello and welcome to another SBSU Math and Physics Resource Center video. My name is Matt and I will be your tutor for today. In this video, we will be doing a calc-based physics problem dealing with conservation of energy and rotation. The thin uniform rod in the figure has length 2.0 meters and can pivot about a horizontal frictionless pin through one end. It is released from rest at an angle theta equals 40 degrees above the horizontal. Use the principle of conservation of energy to determine the angular speed of the rod as it passes through the horizontal position. Okay, so the first thing we're going to want to do is to write out our conservation of energy equation. So that's change in potential energy plus the change in kinetic energy is equal to 0. And the reason we can use this equation is that there are no non-conservative forces in this situation. The pin here is frictionless, and the only force on the rod is going to be gravity. Now we're going to have two types of energy for this problem, and those are going to be gravitational potential energy and rotational kinetic energy. So let's write that out. We've got UG final minus UG initial plus KR final minus KR initial. And that's going to be equal to 0. If we look at the figure up here, I'm going to define this as y equals 0. So our potential energy at this horizontal position is going to be 0. And our potential energy at the initial position is going to be defined as mg times h, where h is this distance here from the center of mass of the rod to the y equals 0 position. So we can start writing out some of these values. The potential energy at the end is going to be 0. The potential energy initially is going to be mgh. The rotational kinetic energy at the end is going to be 1/2 I omega squared. And the kinetic energy initially, since we started at rest, is going to be 0. So now we can rewrite our equation to solve for the omega, which is our angular velocity. So we have 1/2 I omega squared equals mgh. And then from there, we just divide by 1/2 I. So omega squared is equal to 2 mgh over I, and just take the square root of both sides. So we get omega is equal to the square root of 2 mgh over I. So now all we have to do is figure out what h is and what I is. And h being much simpler to do, we'll do that one first. So if we redraw this, we have the side h here, and we have a right triangle. And the center of mass of a uniform rod is going to be at the center of the rod. So this distance here is going to be L over 2, or 1 meter. Now, from trigonometry, we know that sine of theta is going to be equal to the opposite over the hypotenuse. So our opposite is h, and our hypotenuse is 1. So in this case, our h is equal to sine of theta. Our last thing we have to find now is I, or the rotational inertia of our rod. So to do that, we need to do a little bit of calculus. So I, the rotational inertia, is defined as the integral of r squared dm. In this case, our rod, the mass distribution is just a single line, so we're going to use R is x, and dm is going to be defined as lambda dx, where lambda here is our linear mass density, and since this is a uniform rod, we have m, the mass of the rod, divided by L, the length of the rod. So now, if we want to find I, we're going to have to integrate over the distribution starting at the pivot point. So from 0 to L of x squared times m over L dx. And we can pull m over L out of the equation, or the integral, sorry, and then integrate x squared dx. So what we're going to get is m over L times 1/3 x cubed from 0 to L. And what that's going to give us when we plug everything in is that's going to give us our I is going to be 1/3 ml squared. Now, if you recall, our omega was equal to the square root of 2mgh over I. And plugging in what we now know, h is sine of theta and I is 1/3 ml squared, we can get omega is equal to the square root of 2mg sine theta over 1/3 ml squared. And if you notice, the masses cancel out. So they didn't give us a mass for this problem, but they didn't need to. So we can clean this up a little bit with omega being the square root of 6g sine theta over L squared. Now, if we plug in all of our values, g being 9.8, theta being 40 degrees, and L being 2 meters, we come out with an answer of 3.07, or roughly 3.1 radians per second. And that is going to be our angular speed. I hope that was helpful. Thank you for watching, and we will see you in another video. Bye.